Have you ever wondered how buildings can withstand the immense force of an earthquake? In this video, we delve into the fascinating world of earthquake-resistant design, exploring the principles and innovative techniques used to build structures that stand strong even in the face of seismic activity. The ground beneath our feet can shake with incredible force. But what if our buildings could stand firm against nature's fury? Join us as we uncover the secrets of designing earthquake-resistant structures, ensuring safety and protecting lives during these devastating events. Earthquakes in India, particularly in earthquake-prone zones like the Himalayas and the northeastern region, can have devastating impacts, including structural damage, ground rupture, and tsunamis. These events can lead to loss of life, economic disruption, and damage to infrastructure and the environment. Buildings and other structures can collapse due to ground shaking, leading to casualties and economic losses. Earthquakes can cause the ground to rupture, leading to vertical or horizontal displacement, damaging roads, pipelines, and other infrastructure. Undersea earthquakes can trigger tsunamis, which can cause significant damage to coastal areas. Soil can liquefy, especially in areas with waterlogged sediments, causing ground to behave like a liquid and leading to further damage. Broken gas lines and electrical wires can ignite fires, exacerbating the damage from earthquakes. Earthquakes can disrupt businesses and industries, leading to economic losses and job losses. People may lose their homes and livelihoods, creating economic hardship and social unrest. Earthquakes can damage hospitals and infrastructure, impacting public health systems and the ability to respond to the crisis. Seismic waves are vibrations that travel through the earth, often caused by earthquakes, but also by volcanic eruptions, explosions, and landslides. They are crucial for understanding the Earth's internal structure and can be categorized into body waves and surface waves. Seismic waves are responsible for the shaking felt during earthquakes. They provide valuable information about the Earth's structure and composition, including the presence of different layers and materials. The speed and characteristics of seismic waves can be used to determine the location of an earthquake's epicenter and the type of materials beneath the surface. Tidal forces are gravitational forces that cause bodies to bulge or deform due to uneven gravitational attraction. This difference in gravitational pull between different points on a body, relative to a distant object, like the moon or sun, causes the body to be stretched. Research team reveals how tidal forces affect seismic wave. Seismic and tidal forces can impact earthquakes in a few ways. Seismic forces, which are the forces that cause earthquakes, can trigger them by applying stress to fault lines, which can then cause the rocks to move and release energy. Tidal forces, on the other hand, can contribute to earthquake activity by adding to the stress on fault lines, particularly in areas where magma chambers exist or where ocean loading affects the crust. Earthquakes are caused by the release of stress that has built up along fault lines. When the stress exceeds the friction between the rocks, the fault line fractures and the rocks move, releasing energy in the form of seismic waves. Seismic waves from one earthquake can travel through the Earth's crust and trigger another earthquake in a different location by adding to the stress on a nearby fault. The gravitational pull of the moon and sun creates tidal forces that can exert stress on the Earth's crust, especially in areas where there are magma chambers. Seismic forces are the primary drivers of earthquakes, causing fault lines to move and release energy. Tidal forces can act as a secondary trigger, adding to the stress on fault lines and potentially triggering earthquakes, especially in certain geological settings. Tides can cause fluctuations in fluid flow and microseismicity in submarine hydrothermal systems. Some studies suggest that high tides may favor thrust-related earthquakes, while low tides may favor normal fault-related earthquakes. Real-world examples for earthquake designs of new buildings and structure. Design which can withstand the atmospheric pressure and various hazardous weather conditions. Real-world examples of building and bridge designs showcase how engineers utilize various structural systems to meet specific needs and environmental conditions. Buildings, for instance, can employ load-bearing walls, steel frame structures, or reinforced concrete systems, each influencing the building's shape and functionality. Bridges, similarly, may be designed as beam bridges, arch bridges, suspension bridges, or cable-stayed bridges, with each type offering unique advantages for spanning different distances and terrains. Buildings with load-bearing walls, typically made of brick or concrete, distribute weight directly to the foundation. Steel frame buildings feature a skeletal structure that supports the building's weight, offering flexibility in design and large open spaces. Simple beam bridges support loads through horizontal beams resting on supports, commonly used for shorter spans. Arch bridges utilize curved structures to transfer weight, distributing it effectively across the bridge's span. Suspension bridges use cables anchored to towers to support the bridge deck, allowing for long spans and efficient weight distribution. Cable-stayed bridges employ diagonal cables connected to towers to support the deck, offering flexibility in design and long spans. Cantilever bridges use pillars anchored to the ground, with the structure extending outwards from each pillar. How to save ourselves from earthquake, new technologies, and earthquake engineering. How to predict earthquake in advance to save ourselves. To protect oneself during an earthquake, one can adopt earthquake-resistant construction techniques, like using shock absorbers or flexible foundations, and follow safety procedures like drop, cover, hold on. New technologies like seismic invisibility cloaks, shape memory alloys, and disaster response tools like drones and satellite-based alerts offer improved earthquake resilience and preparedness. Drones, used for damage assessments, locating survivors, and creating 3D maps of affected areas. Satellites provide real-time information on damage, assess aftershock risks, and aid in communication and navigation. Mobile app alerts, systems that send out early warnings to users via mobile devices. Smart infrastructure, using sensors and data analysis to monitor building health and predict potential damage.